All right, let's talk about 7.3 sample means. Harvard College Alcohol Study finds that 67% of college students supports efforts to crack down on underage drinking. Does this result hold at a large local college? To find out, college administrators survey an SRS of 100 students and find that 62 support a crackdown on underage drinking. Suppose the proportion of all students that attended this college who supported a crackdown 67%, the same as the national proportion. What is the probability that the proportion in an SRS of 100 students is 0.62 or less? So, first things first, we need to do our 10% rule. So, of course, 100 students is less than 10% of all college students. So it meets the 10% rule, so we can find mean and standard deviation. Our mean, mu of p hat, which is p, which is a 0.67. That's what we're looking at up here, that we're pretending that is our proportion. Our standard deviation would be our proportion times 1 minus proportion over the sample size. Our standard deviation is 0.0470 if we calculate that. To see if it's normal, we have to do the tens. So 100 times 0.67, 100 times 0.33. Of course, 33 is bigger than 10, so it's 67. So the sample distribution is normal, and we can do it. So we're looking at the proportion of p hat that is less than 0.62. So it's right in our calculator. Normal CDF. Lower is negative infinity. Higher is 0.62. Mean is 0.67. And standard deviation is 0.047. And we should get about 14%. All right, we'll move on. Central limit theorem. It draw an SRS of size n from any population with mu and finite standard deviation. The central limit theorem says that when n is large, the sample distribution of the sample mean x bar is approximately normal. Oh, I'm back on. Sorry about that. What are the conditions for sample proportion to be normally distributed? The tens. NP is greater than 10, and times 1 minus p is greater than 10. However, the sampling distribution of a mean is approximately normally distributed if, and really, this, I don't have a pen that works. That is going to give us the fact that we can find mean and standard deviation. Then, either the population distribution is normal, or n is greater than or equal to 30. If it's not normal, we can't do it yet. To find, so our mean is going to be mu of x bar, which is just mu. So the estimated mean. Standard deviation is the standard deviation from the sample, or I guess from the population, divided by the square root of the sample size. So one of these have to happen for it to be normal. This first thing has to be true so we can find the mean and standard deviation. So let's tackle some problems. Lightning strikes. The number of lightning strikes on a square kilometer of open ground in a year has mean 6 and standard deviation 2.4. The National Lightning Network uses automatic sensors to watch for lightning in a random sample of 10 1 square kilometer plots of land. What are the mean and standard deviation of the sample distribution of x bar, sample mean number of strikes per square kilometer? So our mean is going to be what they gave us, 6. And sigma is going to be what their sigma was, 2.4 over square root of 10, and we get 0.75895 for our standard deviation. But we didn't do the 10% rule. Keep picking up the wrong pen. The 10% rule, of course, says that n has to be greater than or equal to 1/10 of capital N, the whole population size. I think we can agree that 10 1 square kilometers is less than 10% of land. Should have stated that beforehand, but that's okay. Explain why you cannot safely calculate the probability that x bar is less than 5 based on a sample size of 10. Well, since 10 isn't equal to 30 or greater than, and the population is not normally distributed, neither is the sampling distribution of the mean. Suppose the NLDN takes a random sample of n equals 50 kilometers instead. Explaining how the central limit theorem allows us to find the probability that the mean number of lightning strikes per square kilometer is less than 5. Then calculate this probability. Since n is equal to 50, and 50 is greater than 30, the CLT, central limit theorem, tells us that the sampling distribution is normal because the sample size is large enough. Mu x bar is mu, which is 6 still. Our standard deviation is the population standard deviation, 2.4, over the square root of our sample size, now 50. Clearly, 50 kilometers is less than 10% of all land. So we can find our mean and standard deviation now. We already did. And the 10% rule checks out as well. So we're trying to find the probability that x bar is less than 5 with a mean of 6 and a standard deviation of 0.339411. We shaded in here, got my standard deviation here, got my mean, got my parameter that I want to check, the 5, and it's 0.00168. Very low probability. I don't know what's going to say there. Suppose the NLDN takes a random sample of n equals 100 square kilometers instead. Find the probability that the mean number of lightning strikes per square kilometer is less than 5. Again, clearly 100 kilometers is less than 10% of all land. So we can find our mean and our standard deviation. Now it's 0.24, so it's going down. It's getting more less biased. It's getting closer and closer to what we want. So, and we have, it is normal because the tens, oh no, because our sample is greater than 30, just like we had up there. So the probability of x bar less than 5 is normal CDF. Lower bound is negative infinity. Higher is 5. And standard deviation 0.24 with a mean of 6. There is a 0.000015 chance of getting lightning strikes per square kilometers less than 5. So what does a bigger sample size change and how? A bigger sample size decreases standard deviation. Since the mean is not in our shaded area, the probability goes down. If we were looking at this part of it, the mean's in there, so that would be going up. How many square miles would the area need to include so the standard deviation of the sampling distribution of the sample mean is 0.1? So we want to know the sample size if the standard deviation of the population, 2.4, divided by the square root of the sample size is equal to 0.1. We want a 0.1 standard deviation. So we have this little equation, and it's just off our formula sheet. We can cross multiply and divide, but really what we're doing is we're switching the 0.1 and the square root of n. Then we square both sides. So n equals the square of 2.4 divided by 0.1, which of course is 576. So we need 576 miles so the standard deviation is, and the sample mean is 1.1. A company cereal box is advertised 9.65 ounces per cereal. In fact, the amount of cereal in a randomly selected box follows a normal distribution with mean of 9.70 and standard deviation of 0.03. What is the probability that a randomly selected box of cereal contains less than 9.65 ounces of cereal? So we have our mean, we have our standard deviation. Here, we're just dealing with mu and sigma. It's not a sample. So our mu is the 9.70. That's what they told us. They have a sigma of 0.03. That's what they told us. And we're using those because we're trying to save one. We're looking for one box of cereal that has more than 9.65 ounces or less. So the probability of x bar less than 9.65 is approximately 0.047779. So not very likely. So it doesn't really help us too much. Now, if we take an SRS of 5 boxes, what is the probability that the mean amount of cereal boxes, or X bar in this box, is 9.65 ounces? Again, 9.65 is pretty close to our mean. And if we take a bigger sample, or actually take a sample, mean stays the same. Standard deviation now is 0.03 divided by square root of 5. So it basically cut our proportion, or our probability, standard deviation, down to half of what it was. So the probability that X bar is less than 9.65 is not very likely. 0.000097. So should we have, well, gotta read the question again. They just asked us probabilities, I suppose. But they advertised that they have 9.65 ounces of cereal. It's very unlikely that they would have that. They're lying to us, and we want our cereal.